This video is about the independence of random variables. Particularly we're gonna discuss cases involving two random variables. Suppose we have two real values random variables x and y. They both map outcomes from the sample space S to numbers from the real line. It's natural to think those two random variables they are independent if knowing the events generated by one random variable does not change the distribution of another one. But how do we formulate those ideas in mathematical formula? So we already know that events of this type will determine the distribution of real valued random variable x, right? So the probability values of events of this type will determine the whole distribution of random variable x. They will only need to forecast events of types of this type. Second, we also know the independence of two random events would mean that those events, the probability value of drawn events A and B need to be equal to PA times PB. If so, we would say A and B, they are independent. Then combine the idea from those two knowledge we have already learned. If events x smaller or equal to x for arbitrary choices of x is independent from events of this type, then the distribution of x will be independent from the distribution of y, right? Given those events will solely determine the distribution of x and y. So that is the idea how we proceed. Essentially, we look at events of type x or smaller or equal to x and y smaller or equal to small y with xy arbitrarily chosen from real line, and we require they are all independent from each other. In this way, knowing what happens to an event generated by y does not change our understanding of the distribution of x, right? Because suppose if we know event y smaller or equal to y occurs, if we know this event occurs, well, it's gonna independent for all the other events of this type anyway, for arbitrary choices of small x, right? So the probability with respect to this type of events remain exactly the same. Therefore, the distribution of the real values random variable x also remain the same. So knowing what happens to y does not change the distribution of real valued x. And vice versa. It goes also the other way around. If knowing what happens to x will not change the distribution of y. So here, indeed, we're gonna make use of this formula to define the independence of random variables, of two real valued random variables. Well, sometimes we might use different notations, but essentially they mean same thing. For example, sometimes we drop the curved brackets, and the probability p x capital X smaller or equal to small x is exactly the same as the notation expressed here. And sometimes we also use comma to denote the cap. So this also denote the joint event of x smaller or equal to x and y smaller or equal to y. Those are just different notations, but they mean exactly the same thing. So summarize what we have just discussed a little bit. Real valued random variables, they are independent if this formula in color red holds true for any choices. Well, this formula need to hold for any choices of x and y from real values, from the real line. Okay, so independence still means products. And because we have many events of the type x smaller or equal to x and y smaller or equal to y, and independence would simply imply products involve all those events. Okay. which is essentially this formula in color red. These are abstract concepts. Let's take a look one example to get some idea. So let's denote x1, x2 as the outcome of two flips, right? xi equals 1 if we have the head, and otherwise is set to be 0. So this is a whole sample space. Here I use 0 to denote tails, 1 denote head. Those are 4 possible outcomes if we throw a coin twice. Each outcome is equally likely to occur. So it's actually quite easy to check this one holds true. Well, not that easy, but you can pause the video here and see if you can check this one or not. Okay, now let's start to check this formula, whether it holds true or not for the above case. So let's first consider the case that the minimum value of x, small x and small y is negative. So apparently on the left-hand side of this equation, we will have 0, because if either or y takes negative values, then we know we don't have any outcomes satisfy that request, right? So at least one of these two on the right-hand side will be 0. So 0 times anything is still 0. This holds true. Next, let's consider something slightly complicated. You can also pause the video here and to see if you can finish the rest discussion. So now let's consider the minimum value of x and y is larger or equal to 0. The first case scenario, let's discuss the case that x is strictly smaller than 1, but also, of course, is non-negative. And y also takes value from the same range. Then how many outcomes would satisfy these requests? Apparently only 0, 0, right? So that's gonna be 1 over 4. And given small x is strictly smaller than 1 and y is strictly smaller than 1, only possible value could be taken by x1 and x2 are 0, so it's 1/2 times 1/2. This holds true, right? Now let's consider another case. Suppose now x still takes the same range, but y is larger or equal to 1. Then there are 2 outcomes out of 4 satisfy the request, which will be 0, 0 and 0, 1, right? Because now smaller y is strictly is larger or equal to 1. So it's 2 over 4. And here what we can say is 1 over 2, right? x1 can only take 0 again, but for the second one, it's gonna be 1, right? It can take either 0 and 1. Now let's consider x is larger or equal to 1, y is within the range 0 and strictly smaller than 1, then it's 1 over 4, and 1 times 1 over 2, right? Again, equal to each other. And the last case, let's consider both x and y, they are all larger or equal to 1, then both sides equal to 1, and the right-hand side equals 1 times 1 and still 1. So indeed, for all possible combinations of small x and y, this formula holds true. So according to the definition of the independence, indeed, the definition is consistent with our intuitions, right? x1 and x2, they are independent. And suppose this equation holds true, it's easy to check this one also holds true. So knowing what happens to an event generated by x2 does not update our understanding of the probability values related to events generated by x1. Right? It's easy to prove for this one. You can pause the video here to see if you can figure out yourself. By definition of conditional probability, the right-hand side, the left-hand side is equal to this, divided by the probability of x2 smaller or equal to y. And according to this formula, we can plug in the product here. And the probability of x2 smaller or equal to y will cancel each other, and indeed it links to the right-hand side of this identity. And this holds true for any arbitrary choices of x, but here we require y to be larger or equal to 0 in order to make sure this event, x2 smaller or equal to y, is a non-zero probability event, because only with this one to be non-zero, to be of non-zero probability, the conditional probability is well defined, right? However, here we are dealing with, well, discrete random variables, right? We know for discrete random variables, the distribution can be determined in an easier way. And indeed, there is also an easier way to determine the independence among two discrete random variables. All we need to do is to look at events of type x equal to small x and y equal to small y, with xy arbitrarily chosen from the support of these random variables. Let's revisit the example and see what happens. Right now, it's much easier to check this formula in color blue, right? Now we only have 4 combinations to go, right? So small x can either be 0 or 0, 0, 1, and 1, 0, 1, 1. So in all those cases, if you look at those 4 outcomes, right, the probability of x1, for example, equal to 0, x2 equal to 0 is 1 over 4. For the second case, also 1 over 4, 1 over 4, 1 over 4. And the right-hand side of this equation is always 1 over 2 times 1 over 2. This all holds true indeed. And it's also easy to check as long as we have this formula in color blue, holds true for all possible choices with small x and y from support of those random variables. We can also have this result that as long as this holds true, it will imply this for sure. So knowing what happens to discrete random variable x2 does not update our probability values of events generated by x1 and vice versa. Okay, it's easy to prove. You can try it yourself. So to summarize a little bit, real valued random variables xy, they are independent if this holds true, right? If this formula in color red holds true. So the probability of drawing event x smaller than a small x, capital Y smaller or equal to a small y, equals the product of px smaller or equal to x and p of the event y, capital Y smaller or equal to small y. For discrete random variables, there is an easier way to check the independence. As long as their probability values satisfy this equation, we will say those are independent. Those two random variables x, y are independent. Okay? But the second formula only applies for discrete random variables. The first one is a little bit complicated, but it holds true for more general case, for real valued random variables. Those concepts can also easily extend it to conditional independence. This extension exactly like the extension from independence of random events to conditional independence of random events. So here we say real valued random variables x, y, they are conditionally independent given discrete random variable z if this formula in color red holds true, right? So conditional on whatever event generated by z, so here is z equal to z. This conditional probability of drawing event is equal to the product of the conditional probability of x smaller or equal to x conditional on the same information set, and times the probability of y smaller or equal to y conditional given the same information set, right? Actually, when you have this equation, you can show that if we already know what happens, if we already learn this event occurs, then knowing what happens to event generated by y does not update our understanding of the probability values of events generated by x. So from this formula in color red, you can easily show results like this. So indeed, x, y, they are conditionally independent given z. Because if we already know what happens to z, knowing y does not update our understanding of probability values related to events generated by random variable x. And vice versa, right? Knowing, if we already know in z, knowing what happens to x does not update our understanding of probability values related to events generated by random variable y either, okay? And similarly for discrete random variables, right, we have an easier way to check whether they are conditional independence or not. Similarly to independence among events, these concepts can also be generalized from 2 random variables to n random variables, following the similar logic. Now, those are abstract definitions or results. Let's take a look at some examples. The examples gonna show that conditional independence and independence exactly similar to what we have already seen in conditional independence and independence relating to random events. Here, when we consider random variables, those two independence are not implying each other either. So let's first consider this example to show that conditional independence does not imply independence. Suppose we're gonna play against one of 2 identical twins for 2 rounds, right? You're gonna flip a coin to determine which game you play or which twins you're gonna play against. So in game A, you're gonna play against first twin and you are evenly matched for 2 rounds independently. Well, for game 2 against the other, you win with probability 3/4 for 2 rounds. Let's denote x, y, they are outcome of rounds 1 and round 2. There are no hot hands, right? So x, y, they are independent. Z equal to 1 if you play against A, otherwise Z equal to 0. Now we conditional on Z equal to 1 based on the background story x, y, they are IID Bernoulli distribution. Here IID is short for identical independent distributed, right? IID means the first one means they follow identical distribution. So the distribution is exactly the same. They are both Bernoulli distribution with successful rate 1/2. The second one is independent distributed. So these two, x and y, they are independent, okay? Then conditional on z equal to 0, x, y, they are also independent. So we have conditional independence here. Well, in the second case, they are independent but with a different successful rate. So now the successful rate increases a little bit, that's 3/4. However, they are not independent from each other without conditioning on that. Because we're gonna have this result that knowing x equal to 1, knowing this event generated by random variable x equal to 1 happens, the probability that you're gonna win the second round is much larger than the original probability. So apparently, even though x, y, they are independent, conditional independent, given the discrete random variable z, they are not independent from each other. And this can be easily checked, right? So you can pause the video for now and think how to calculate this conditional probability and this unconditional one. Now, for the unconditional one, right, you have half probability because you're going to flip a fair coin to determine which game you play. Half probability you play game A, where you have successful rate equal half, and half probability you're going to play game B, for which you have 3/4 successful rate to win the second round. So in total, that's 0.625. For the second case, by definition, this is the probability of y equal to 1 and x equal to 1, this drawn event to happen, right? Divided by the probability of y equal to 1. So the numerator is, well, it's half possible, half chance you play against twin A. So that's, and you win both both rounds. That's 1/2 to the power 2. Half chance you play game B, play against another twin, and win both game, you with this successful rate. That's 3/4 to the power 2, right? You have to win both rounds. So together is 0.65. Indeed, this conditional probability, conditional x, is larger than probability value of y equal to 1. So x and y, they are not independent without conditioning on that. Because knowing what happens to that apparently update our understanding of probability of events generated by y. So in short, conditional independence does not imply independence. Right? Can you think about one example to show that independence does not imply conditional independence either? Here's a hint: coin flip. Right? You can pause the video here and think if you can figure it out yourself. Okay, now we could think about flipping two coins. And we're gonna let xi equals this indicator function ai. So indicator function ai basically means it maps s to 1 if s is from this event ai, and 0 if it does not from the event ai. So here basically means xi equals 1 if the s flip is a head, right? And otherwise it's a 0. Because we are flip two coins, apparently, well, x1 and x2 are independent. Now, if it denotes that as the summation of these two, you'll find out x1 and x2, they are not conditionally independent given that. And it's easy to check that. Because suppose we already learned z equals to 2. So suppose we already learned z equals to 2. And x2 equals to 1. What is this conditional probability? It has to be 1, right? Because if z equals to 2, x2 equals to 1, x1 has to be equal to z minus x2, which is 1. So this one equals for sure, which is not equal to the conditional probability of x1 equal to 1 conditional on z equal to 2, which here is equal to half, right? If you think about all possible 4 outcomes, we only have 0, 0, 0, 1, 1, 0, and 1, 1, those 4 outcomes, right? If we know z equal to 2, and the probability, so we know oh, sorry, I made a mistake here. Let's consider this case, right? Let's consider the case z equal to 1. Okay. If we conditional on this case, z equal to 1, then this conditional probability given x2 equal to 2, x2 equal to 1 as well will have to be 0, right? Because x1 can only be equal to 0 in this case. Otherwise, their summation will not be equal to 1, which is certainly not equal to the case without knowing the event of x2 equal to 1 occurs, right? Because conditional on the event that z equal to 1, the probability of x1 equal to 1 will be half. Consider we have the 4 events over there, right? Both of these two outcomes will lead to the fact that z equal to 1. If I use 0 to denote tails and y denote heads. And if this happens, right, with half probability, x1 will equal to 1. So here, apparently, given z equal to 1, knowing what happens to x2 change our understanding of the probability values of x1 equal to 1. So x1 and x2, they are not conditionally independent given that. In this case, independence does not imply conditional independence. So conditioning and independence are not easy. Hope this makes things slightly clear after you watch this video. And thank you for watching this video.